Hello everyone, welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked mathematics questions at both the high school and university or college levels. If you're interested in getting help with some tutoring, or if you're interested in getting some help with your homework, check out the links in the description below. Cool, so I'm gonna switch my screen real fast. And we can get right into this mathematic magic. Okay, so the first question that we have on our menu today is asking us if we could possibly simplify the expression natural logarithm of 5. Okay, so are we able to simplify this? The short answer is no, but we could also learn quite a lot if we try to identify things that we could look for if we did want to simplify this. So things to look for. To simplify. So the things that we want to generally look for when we are simplifying logarithms, logs, we want to look for coefficients on the logarithms, logs. And when we see a coefficient, we want to convert to powers. Like so. So suppose we have a natural logarithm of x. We want to simplify to make it just ln of x with x to the power of a. Okay, so we want to move those coefficients into the power. But clearly, that does not apply here. Well, if we have a coefficient of 1, and, well, 5 to the power of 1 is 1, so not particularly useful for this case. Another thing that we want to do is addition should be combined. Addition of logs. Okay, so suppose that we have something like ln of x plus ln of y. We'd want to rewrite this as ln of x times y. Okay? Now, same thing can be said with division, but division is going to be associated with subtraction. Should be combined as well. So if we had a situation like ln of x minus ln of y, instead of multiplying them together in their compressed version, you're going to divide them. So it's going to be x divided by y. Okay, so this is how we would typically simplify logarithms, but clearly none of these are relevant to this particular one that we're given, logarithm 5. There's no coefficient, or the coefficient is 1, but that's what we want, and there's no addition or subtraction, so we're kind of stuck here. So this is really as simple as it gets. So when you get it as simple as you can get it, that's when you want to send it to your calculator. So I'll ask my calculator what in the world the logarithm of 5 is. And my result for this is 1.6094. So in this case, we cannot simplify further. Okay, pretty cool stuff. Natural logarithm, it's a fun time. Simplifying them is very necessary when you do have more complicated expressions, but it's not always the case. Sometimes you're already good. So here, the above solution is good. Is good. Awesome. Okay, so here's the next question that we have on the menu today. It is asking us, whoops, sorry to kick the camera. It is asking us, how do we find the value of log 1000? Really what it means is log base 10 of 1000. How do we find this? Let's say that's equal to x, and we're trying to figure out what x is equal to. Okay, really what logarithms mean is like, we are looking for the base to the power of something is going to be equal to 1000, right? So essentially, what we're looking for is 10 to the power of x is equal to 1000. To be more formal about it, we could say that 10 to the power of log base 10 of 1000 is equal to 10 to the power of x. This is like formally like this upstairs here. I mean on the left side, 10 to the power of log 10, log base 10. We're doing that to both sides. So we're putting both sides as the power with a base 10. And the 10 on the base here and the log in the power neutralize each other. So that just becomes 1000. Okay, so that's where this expression comes from. So we're looking for 10 to the power of what is 1000. Okay, so let's think about multiplying 10 together. So if we know that we have like 10 times 10, this is 100. 10 to the power of 2 is equal to 100. But if we multiply by 10 once again, we'll get 10 cubed is equal to 1000. And that's exactly what we're looking for. So 1000 is equal to 10 to the power of 3. And when we go back to here, 3 is occupying the space where x is supposed to be. So we have to know that the result of this has to be 3. With a big happy face. Okay, so these are kind of like a pretty basic rundown of how logarithms work. It means like the base to the power of the result is equal to the argument, and the argument is here. Let's write that out. Argument result, and that's the base. Base to the power of result is equal to argument. Okay, that's like another way to repackage logarithms. It's good to keep this in mind because logarithms are very commonly used across many different areas of mathematics and engineering and science. So stay familiar with them and keep in mind how they work. So here they came to the solution that everything is, or the result is 3. As we can see, 10 to the power of 3 gives us 1000. So everything's good. Cool. Nice. Awesome. Beautiful. Okay. Okay. So here is the next question that we have on the menu today. It is asking us, what is an opposite reciprocal? Okay, well, just from the two-word combination opposite reciprocal, we can see that we have two words associated with them, right? So we have the word opposite and the word reciprocal, right? So let's break this down into their component words, and then we can see what they mean individually, what they mean together, and then how we can use those two together and why is that going to be useful. Okay, so that's going to be our plan of attack. So the word opposite, this means we're going to flip it or inverse the sign or flip the sign. So flip the sign, flip the plus minus sign. So positives become negative, negative becomes positive. That's what we mean by opposite. And reciprocal, well, we flip the fraction. Okay, so opposite reciprocal, let's say x. The opposite reciprocal of this, opposite reciprocal, is going to be negative, that's the opposite part, 1 over x, and the 1 divided by is the reciprocal part. Another way that if you write this is negative x to the power of negative 1. That's another perfectly valid way to write this. Okay, so why is this useful? Opposite reciprocals are useful in action. So they are useful when we are looking for perpendicular lines. Perpendicular lines. The slope of the lines will be opposite reciprocals opposite reciprocals of each other. Okay, so this is like I would say maybe the main reason why we even pay attention to opposite reciprocals in the first place for perpendicular lines. So let's show an example of that in action. Perpendicular. And perpendicular, if you're not aware, it means we have 90 degrees of separation. So basically 2 lines and there's a perfect corner between them. Okay, so if we were to draw out a mathematic grid like this, that is a very straight line for freehand. Good job to me. Oh, that's pretty good too. Steady hands, not bad. Okay, so suppose that we have one line and we can make it a green line, and this has a slope of 2. Or this is a slope of 1/2. My bad. So we can say this one is equal to y equals 1/2 of x. If we wanted to draw something perpendicular to this, we would need negative 2x is equal to y to be perpendicular. Because 1/2, and we take the opposite reciprocal, is going to be negative 2. Okay, so that's why that's going to work out. So if we draw that line, let's do it in red, of negative 2x, we will have a slope that looks like this, or a line that looks like this. So this is y equals negative 2x. And hopefully it should be fairly clear that these lines have to be perpendicular to each other. Like, as you can see, maybe the drawing makes this a little bit not as clear as it should be, but you can see here that we have like 90-degree angles between the red and the green lines, so they are definitely perpendicular to each other, and we know that they have to be perpendicular to each other because when their slopes are opposite reciprocals, or negative reciprocals, another way to say that, we know that they have to be perpendicular if their slopes are negative reciprocals. Okay, so this is how you would use them in action, and you really just multiply by negative 1 and divide it by 1, or raise it to the power of 1, negative 1. Okay, so it's fairly straightforward. It's pretty fun stuff and very useful for slopes. Cool. So the solution is good. Yeah, nice. Cool. Okay, so the next question that we have on the menu today is asking us how many quarts are in a gallon. Okay, so a quart is a measure of volume, and a gallon is a larger measure of volume. So a quart, maybe that could be like, a fairly decent size like bottle of juice, and a gallon, that's like like a like a cooler full of juice. Like, it's quite a bit larger. And well, we know here that we have 4 quarts per 1 gallon. Okay, so knowing this conversion, we can use this term can be used, oops, camera too big, let me fix that real fast, or, aha, okay, this term can be used to change between quarts and gallons. Okay, so suppose that we have x gallons. If we multiply x gallons by 4 quarts per 1 gallon, you can see that we can treat the gallons, or we can treat these units pretty much like they're variables in math. And you can see if we multiply them together, the gallons here on the upstairs of this cancels out with the gallon down here, right? Because anything divided by itself has to be 1, so we can cancel them out. So the result of this is just going to be 4x quarts, which makes perfect sense, right? Because if we know we have 4 quarts in every gallon, let's say we have 5 gallons, we should expect 4 times 5 gallons, we should expect 20 quarts, and that's exactly what our equation shows. This might seem like fairly straightforward, but this is like the type of procedure that you definitely want to follow, especially if you're going into like chemistry or engineering. Cancellation of units is quite important. Okay, now let's say we want to go the other direction. We want to convert quarts into gallons. Like I have 20 quarts of soy sauce. How many gallons of soy sauce do I have? It doesn't have to be soy sauce. It could be water. It could be whatever volume occupying object that you want. But let's say we have y quarts. Instead of multiplying by this term, we want to multiply by the inverse of the term, or another way of saying that is we want to divide by the term. It's better, in my opinion, it's easier to think about it in terms of multiplication, and then you just flip it upside down to represent the division part of it. So if we do, we want to get quarts on the downstairs so that they cancel out. So we know we have 4 quarts down here, and the 4 quarts is of 1 gallon. And, well, we do our quick unit cancellation. Quarts on the upstairs, quarts on the downstairs leaves us only with gallons left, which is what we're expecting to convert quarts to gallons. So this means we will have y over 4 gallons. And this makes sense because let's say we have a lot of quarts, maybe 20 quarts. We'd expect a lower number of gallons because 1 gallon is larger. So 20 quarts corresponds to 5 gallons. Seems like a reasonable thing. Okay, so unit cancellations like this is very useful across many different fields of big brain activities. So yeah, stay ready for this, and stay ready with the unit cancellations. It's very important. All right, cool. So the above solution is good. Better with some examples of conversion. Cool. Okay, so here is the next question that we have on the menu today, and it is asking us, how many sides does a rectangular prism have? Okay, I actually might have a rectangular prism that I could show you on the cam. So I've been building a robot recently, and this robot needs to have like a body to like hold stuff in it. So I have this like a little box here, and boxes, oh, I can't open that box, I stapled it shut. But you know, I have a little box here, and this box is, well, fairly straightforward. You can see it's a rectangular prism. It's got rectangles all around. And let's say if we try to like count how many faces it has, well, we have like one here, one here, one here, one here, and on the top and the bottom. So we have 6. A dice is another example of a rectangular prism. And dice definitely have 6 sides. I've never rolled a 7 on a dice, or never rolled a 7 on a legitimate dice. But let's actually, it's fairly straightforward to see how many sides they have. But I think it's a little bit more intuitive to kind of think about how we could like mentally unfold a rectangular prism, right? So given this diagram, if we wanted to draw an unfolded version of this, we would draw like maybe something like this. Something like that. Okay, so hopefully you could see that this, can you see my mouse? Yeah, okay, so you see these 4 middle rectangles. You can see kind of how they would roll up, kind of like a burrito. And these 2 like squares on the top and bottom, those are going to be like the lid and I guess the floor and the ceiling of this rectangular prism. And the reason why it's useful to kind of have like the mental ability to break down 3D objects into their 2D nets. This is what it's called. A net is like an unfolded 3D object. You cannot make a net of certain things, like a sphere. You cannot make a net without some type of distortion or ripping. But for like prisms, like rectangular prisms, definitely possible to make a net. And this is oftentimes going to be very useful, especially if you get asked how do we find the surface area of this rectangle? Well, you can see that finding the surface area of the entire rectangular prism, you just need to find the area of a couple of different shapes. 6 different shapes. Could be rectangles. Some of them might be squares, but they don't have to be squares. And so having a net can definitely be very helpful in helping you make that calculation. Okay, so we got 6 sides. We got 2 base sides, and every side has like a twin associated with them, and that's like a rule with rectangular prisms. You see how the 2A squares, they have to be twins. Otherwise, well, we're not going to be able to fold this back up. And maybe the B rectangles, those are twins, and the C rectangles are twins as well. So those you're going to have 3 matching pairs. But like in this case, you can see that B and C are actually going to be the same, but that doesn't have to be the case. So in this little box right here, you can see that every side has a twin, but these pairs of twins are not actually twins. Okay, so hopefully that clears things up. We got 6 sides on a rectangle, fairly straightforward, and that's a beautiful thing. So the above solution is good. Cool. Okay, so this is the next question that we have on the menu today, and it's asking us the terminal side of theta, which is the angle. So the terminal side of the angle in the standard position contains the point 3, 0. Okay, how do we find the exact values of each of the 6 trigonometric functions of theta? Okay, so a lot to unpack here. Let's start here. So the terminal side of theta, the angle, in standard position contains the point 3, 0. Okay, so let's draw that out and what that really means. So if we were to draw an XY coordinate grid, forgive my imperfect lines. So if that's the X and that's the Y, I mean, we don't really need to say X, or I guess we do, because you see how its coordinate is like X and Y. So it says our X position is 3, so this is 1, 2, 3. Okay, our x position is 3 and our y position is 0. Well, I guess that just means we're on the x-axis. That means our point of interest is going to be right here. Okay? So our angle, or our thing is definitely going to be looking like this. And our angle, well, the only angle that can make this work, because we measure angle like this way, angle measurement, so the only way that this is going to work out is if it's if the angle is 0 or if the angle is 360 degrees. They pretty much will result in the same math, so it's going to be a lot easier if we just deal with this situation where we just know that the angle has to be 0. So theta equals 0 degrees must be the case if the line is straight and contains point 3, 0. 3 in the x, 0 in the, 0 in the y, yeah. Okay, so, yeah, and that's the terminal side. So this is how we find the angle. So that's the first part of it, is identifying the angle. And then we have to find the exact values of the 6 trigonometric functions for theta. So what that means is we have to find sine of theta, cos of theta, tan of theta, cosecant theta, secant theta, and cotangent of theta. And this is, well, once we find the first 3, we've pretty much found the others, because we just flip them upside down on the reciprocals, and we can get our last 3. So we really just need to find the first 3, which is fairly straightforward. 1 over tan theta. And tan theta is just sine theta over cosine theta. So if we find the first 2, we pretty much got them all. Okay, so sine theta, when theta is equal to 0, so let's draw out what the sine graph looks like. Like this. So sine starts at 0 and it goes like this. Okay, so this is sine theta. And we know sine at 0 has to be 0. Fairly straightforward. Now for cos, cos looks a little different. It looks a little something like this. Cos theta in blue. And, well, as you can see, cos at cos when theta is equal to 0 has to be 1. Okay, so tan, if it's just the sine divided by the cos, it's just going to be 0 over 1, which is equal to 0. Fairly straightforward. Okay, cosecant is just going to be 1 over 0, but you know, you can't divide 1 by 0. Nothing can be divided by 0, so this is undefined. Secant, well, we just take the reciprocal of 1. So 1 over 1, which is equal to 1. Nice. Happy face. And the inverse of tan, well, we have to do 1 divided by 0. So that's another 1 divided by 0 case, which is undefined. Okay, so that would actually pretty much wrap up the entire question. Yeah, once we found sine and cos, everything was good. Everything was good. Okay, so hopefully the answer that we have down here agrees with us. Yep, everything is good. So the above solution is good. Awesome. You just have to pretty much once we found the angle, everything was fairly straightforward after that. But yeah, so just find the angle, knowing the points. Of course, it didn't have to be there if it was If it was like 3 and 4, and it was like maybe up somewhere like here, we would need to calculate that angle first, and that angle would not be 0. But if the angle's not 0, it doesn't really make our life more difficult. We just we would just send that non-zero number into our calculator, or we can do it graphically depending on how convenient the number is. But yeah, it'd be all pretty much the same procedure. Cool. So this solution is good. The above solution is good. Beautiful. Okay. So here is the next question that we have on the menu today, and it is asking us, what is the square root of 45? Okay, so I'll list out like the procedures, and because of course we could just ask our calculator, hey, what's the square root of 45? And the calculator will tell us pretty directly and pretty accurately as well. But a lot of the times it's going to be a lot more intuitive to simplify this if we can, right? So want to simplify phi instead of direct calculation. Some calculators are pretty good and they can automatically simplify this for you, but I'm going to teach you how we can do this just off the power of our noggins. So the first step that we want to do is factor all under root stuff to prime numbers. And then we want to, anytime we want to bring all duplicates outside. Outside of root. Okay, so we know that 45, we have to factor this, right? 45, thinking back to my times table, I can divide it by 5, right? Yep, I definitely can. It ends in 5, has to be divisible by 5. And I know that 9 times 5 is 45. Call that a 9 to 5. Okay. And, but we want to factor it, even the factors that we immediately pulled out, we want to simplify those as well under the same procedure. So we want to factor those into prime numbers as well. 5 is a prime number, so we can leave that, but 9, I know 9 is 3 times 3. So that's going to be 3 times 3 times 5. And that is definitely 45. Do the quick math. 3 times 5 is 15 times 3, 45. Seems reasonable to me. Okay, so we know that we can replace everything with under the root. That 45, we can replace it with 3 times 3 times 5. So root 45 equal to under the root 3 times 3 times 5. And we want to bring all duplicates outside of the root. Okay, so the duplicates in this case are the two 3's. We have a 3, and that 3 has a twin. So these 3, the 3's are going to be brought outside. Oops. But we're only going to bring one of them outside. The reason why is because as it traverses that root, because like the twin 3's together, they're 9, right? So it's like 9 as it leaves the root, it has to get square rooted itself, so it becomes a 3. So the duplicates that we have are the twins fused together into a single child outside of the root. Okay, and that would be our final answer right here. 3 times the square root of 5, and this is going to be a better answer than just like getting the decimal value out of your calculator for this, because sometimes you so this is definitely going to be an irrational number, meaning there's going to be a whole lot of decimal numbers that are going to be quite painful to write out completely. So having a simplified version like this is going to be much easier. And let's to actually get the decimal value. So this is approximately equal to, I'm going to send it through my calculator ASAP fast. So the actual result of this is 6.708204, on and on and on and on. That's a very long number, but you know, sometimes you will need to eventually simplify it down to a decimal version, but you want to keep it in like precise terms like this, 3 times root 5. You want to keep it like that as long as possible to ensure maximum precision. Okay, so yeah, this is good. Very good. Beautiful. So the above solution is good. Good job. Nice. Okay, so the next question that we have on the menu today is asking us the fraction 1 over 24 can be written as the following sum. 1 over 24 is equal to 1/8 of x plus 1/4 of y plus 1/3 of z, and that's all equal to 1/24. Okay, seems reasonable, and it gives us a system of equations, or multiple equations that are related to each other, and you know, they tell us the numbers that could occupy x, y, and z. So we know that x plus y plus z is equal to 1. 2x minus y plus z got to be 0. And we have negative x plus 2y plus 2z is equal to negative 1. Okay, so this is a system of equations, and essentially what we're going to try to do is we're going to try to solve for x, y, and z, and then that should definitely give us like, and this top expression here should ring true once we solve for the x, y, and z just with the bottom 3. Okay, so let's write out our system of equations. So we have x plus y plus z is equal to 1. Let's call this equation A. Equation B, we have 2x minus y plus z is equal to 0. And equation C, we got negative x plus 2y plus 2z is equal to negative 1. Okay, there are many different ways that we can solve a system of equations. The method that I'm going to proceed with is going to be like probably the most straightforward. We're just going to do like repetitive isolate and plug. So I'll call this the isolate and plug technique. Other options include like matrix math. Some calculators are even powerful enough to do this matrix math for you, but that gets into like, it's a little bit more difficult and more delicate, but this isolate and plug technique that I'm about to use should be fairly straightforward. Okay, so what we're going to try to do is we're going to take equation A and we're going to isolate one of the variables. So let's say we try to isolate, actually let's do equation B because we have equals 0 on the other side. So it's going to be a little bit easier to deal with. So equation B, we want to isolate one of the variables. In this case, let's isolate y. So here we have 2x minus y plus z is equal to 0. We could rewrite this by bringing y to the right-hand side, and we'll have 2x plus z. 2x plus z is equal to y. Okay, and it's good to like square these off. Now we want to sub this into one of the other equations. So sub into another equation. Let's do sub into A. Okay, so we know that equation A originally is x plus y plus z is equal to 1. Okay? So this y we're going to replace with this. So it's going to be x plus, instead of y, we know that 2x plus z is equal to y, and that is plus z itself is equal to positive 1. Okay, so that's all cool. So let's simplify. So we have 3x plus 2z is equal to 1. Now we want to follow the same procedure again. So we want to isolate one of the variables. So let's isolate x. Isolate x. So to do that, we'll have to bring the 2z to the other side and divide both sides by 3. So we'll have x is equal to 1/3 of 2, whoops, it's got to be negative. So it's going to be 1 minus 2z. Okay, and that's going to be our x value. Awesome. And given this, we can sub into final equation. In this case, our final equation is C. Equation C. So equation C, we have negative x plus 2y plus 2z is equal to negative 1. So we want to replace y out of here like that. So we can rewrite this as negative x plus 2. Now the y is multiplied by 2, so what we equate it to also needs to be multiplied by 2. So it's going to be 2x plus z, because that was equal to y, plus 2z is equal to negative 1. Okay, so we can expand this out to be 3x plus 4z is equal to negative 1. And that's just by doing 2 times 2x minus x. That's going to be 4 minus 1x, so 3x. And then 2z plus 2z, 4z minus 1. And the x is here. We're trying to isolate this. Substitute x. And we know that x is going to be 3 times 1/3 of 1 minus 2z plus 4z is equal to negative 1. I'm sorry for the Americans who are hearing me right now say Z for the last letter in the alphabet. I'm from Canada, so Canada we say the letter Z. I know Americans like to say Z, but I'm sorry. Please accept me. Okay, so you can see the 3 on the outside and the 1/3 here. They neutralize. So they become 1. So let's give them a little x out. So all that we are left with is 1 minus 2z is plus 4z is equal to negative 1. And combining all of our like terms, we have 2z, because that's the 4z minus 2z, and then bring the 1 to the other side, it becomes negative, so we have negative 2. So z has to be negative 1. Okay, so we found one of the numbers. That's beautiful. Now that we have this number, z equals negative 1, I'll do a different color so it's more clear. We can go back up to here, and we sub that back in. So x is equal to 1 over 3 times 1 minus 2 times negative 1, because that was z. So x is going to be equal to 1/3 inside the bracket, 2 times negative 1. That's going to be 1 plus 2. So that's going to be, as a result, 3 in here, and then x has to be 1. Okay, now that we know x and z, well, equation A can pretty quickly tell us what y is going to be. So if we know that x plus y plus z is equal to 1, we could have used any of the equations here, but this was just like the one that was right in front of me and the most convenient. So we know that x has to be 1 plus y. Y is, well, we don't know y, but z, we know that we have -1. That's equal to 1. Hey, this cancels out with that, so y is equal to 1. Okay, so this will be the result of our system of equations analysis. So x, y, z. X is 1, y is 1, z is -1. Hopefully we would come to the same conclusion here. Z -1, y is 1, x is 1, awesome. And yeah, so that means now that we found these, and the original question was asking us like 1/24 is equal to x over 8 plus y over 4 plus z over 3. And now I want to sub these in to check if this is going to be actually well, true or not. 1/24. So x is equal to 1, so 1/8, plus y is 1, so 1/4, plus -1, which is z, over 3. And we want to make to make this true, let's take the right hand side and make them all denominator 24. All squiggly over 24. So this will be 1/24 is equal to 24 is 3 times 8, so 24 plus 6/24, because 6 times 4 is going to be 24, minus 8/24, right? Because 8 times 3 is 24. Now that all of them have the same denominators, we could see that we have 3 plus 6 minus 8. So that's 9 minus 8. That's 1/24. So 1/24 equals 1/24 equals big happy face, because that means that we have definitely solved, we have correctly identified x, y, and z, found their real values, and subbing it back in. With this system of equations, everyone is satisfied. You sub in x equals 1, y equals 1, z equals -1 to any one of these 4 equations, and everything's good. So yeah, this solution is awesome. We came to that same conclusion of x, y, and z, and we proved that it's got to be good. The golden rule here is that the number of equations has to be greater than or equal to the number of unknowns, or the number of variables. And this must be true to be solvable. Must be true to be solvable. If that is not true, you can't solve it. You can only have like you'll have equations for like one variable is a function of another variable. So yeah, assuming this is true, everything else will be solvable and everything else will be good. So yeah, cool. So the above solution is good. Beautiful. Good job. High five. Okay, so the next question that we have today is asking us, what is the square root expression as an imaginary number of the square root of 64? Pretty much what it's asking is, what is this? Okay, now, sometimes in earlier math education, people will tell you, you can absolutely not take the square root of a negative number. And that is kind of a reasonable thing to believe. Like, you know, ask your calculator, what's the square root of a negative number? And it's going to say error. It's like, okay, I guess error is the answer. Yeah, there's no real number answer, but a long time ago, there were some very smart people that said the math that we have already is not difficult enough. Let's make it more difficult by making imaginary numbers. That's not actually the reason why, but we have imaginary numbers that are a little bit more complicated. They're also known as complex numbers, but they're nothing to be scared about. So the fundamental relationship is that we just said, you know how we said we can never take the square root of a negative number? Forget that. I'm just going to say we can, and we always will be able to under the following principle. If we just say the square root of -1 is equal to I, or if we say I squared is equal to -1, knowing this, all of a sudden that rule of no negatives under the root, we get rid of that rule. We are big kids now. We can handle that now with this fundamental relationship. Okay, so essentially how we do this is, as we know, we can factor out things that are under the root. So what happens if under the root here we factored out a -1 times 64? Well, another way that we can rewrite this is the square root of -1 times the square root of 64. Hopefully, all of us are well familiar of the fact that 8 times 8 is 64. So, you could also write this as -1 times 8 squared. We're not really going to worry about plus minus right now. Let's just worry about like the absolute value. Okay, so given here, we know that square root of -1 is going to be I, and well, the square root of 8 squared, well, that's just got to be 8. But oftentimes we prefer to write it as 8I, because I is kind of like a variable, and it's kind of nice to treat it that way. Okay, yeah, cool. So 8I is going to be the result of this. And as long as you keep in mind the fundamental relationship that the square root of a -1 is equal to I, and then you factor out the negatives when you have negatives under the root, everything will be good. And if you ever square the I, just make sure it becomes -1. Okay, so all of that is cool. And it would be more formal to say this is actually like plus minus, because really what it could be is -1 under the root of -8 squared. So because of that, we want to incorporate the plus minus. Okay, so it's not like always super important, but sometimes if you ever get like inconsistencies, that could be a reason why. Okay, so the above solution is good. Answer be better with plus minus as -8 and +8 are the square root of 64. Cool. Okay, so the next question that we have on the menu today is asking us, what in the world is an arc length? Okay, so arc lengths are typically associated when we have circular things or curved lines. Okay, so let's see if I can get a circle here. Circle. Cool, nice circle. Okay, so if this is the center of the circle, the arc length is, given certain bounds, it's like, well, the length of the arc. So I know that kind of sounds ridiculous, but it'd be a lot more clear if I draw this out. Okay, so suppose that we have a situation like this. Here we have our angle. This distance from center to edge is going to be the radius. The arc length is going to be, in red pen, right there. So this is the arc length. And this is typically represented with S. We don't use A, R, or R is used for radius, and we're not going to use A because that would be way too easy. It's more like because A is commonly used for other things, but yeah. So this is what the arc length is. So if you were asked a question like, if this angle is, if you're given a certain angle, what is the length of its arc? Well, to calculate that, you would be, so if we say that given angle, find arc length, you would just do angle over 360 degrees multiplied by 2 times pi times radius. Okay, so this would be your S of theta. The reason why this works is, well, this is going to be this term. This first term is the percentage of full circle, and this here is circumference. So hopefully it should be hopefully clear from the diagram here that the arc length is going to be some fraction of the total circumference of a circle. For more, I guess, complicated curves like ovals or waves, we're not really going to worry about arc length that much, but if you know the total circumference, which has got to be 2 times pi times r, that's the definition of circumference. If we know the angle, well, we just take the percentage of that and we can find the corresponding arc length. Now, a good relationship between arc length and radius and theta is as follows. So theta is equal to arc length over radius. Okay, and this is the angle in radians. Arc length and radius. Okay, so this is like the definition for radian angles. And this is extremely important. You will use it in quite a few different areas of mathematics as well as engineering and science. Radian knowledge of angles is very important. Now, I'm going to give you some secret sauce on a great way to remember this is you want to think of an eye, right? So, this like tear duct that we have that, it cries tears when we're having sad times. Let's not draw that tear because we're happy right now. And, if we have an eye like this, so this could be represented the S, the arc length. This tear duct, kind of like, the theta symbol, angle in radians, is going to be there. And the circle in the pupil of the eye is going to be the radius. Okay, so I like to think about an eye to do this, because like just from the eye you can see that like this is equal to eyebrow, which is S, over circle, which is corresponding to R. I feel like that's how I remember it, is I just think of an eye and this tear duct. Okay, so yeah, it's sometimes it's great to kind of look for external objects. Like I always have my eyes with me; they're kind of attached to my head. So having things attached to you and trying to like conceal equations inside of them, it could be definitely be a useful thing, especially like, you know, if you're in a pinch on a test and you're trying to remember, oh, how do I find the radiant angle if I know the arc length and the radius? You know, you just think, oh, well, pull out my eye, think about it. Yeah, okay, so it's quite useful. Nice. And yeah, so that would be that. So the above solution is good. Okay. This is the next question that we have on the menu today, and is asking us, how do we find the exact value of arctan, or inverse tan, of root 3? So tan -1 of root 3, or inverse tan, it's arctan. Let's just say that this is equal to theta, because we know that if we take the tan of both sides, the inverse of this is going to be 3 is equal to tan theta. And we know that tan theta from our SOHCAHTOA has to be opposite over adjacent. Op over adjacent. Okay, so essentially, if we have a right angle triangle like this, let's call this op adjacent, and that's theta. We know that op over adjacent is equal to root 3. And if we have adjacent equal to well, pretty much we have this relationship, and if we set one of the numbers, like, you know, because we can scale triangles, we can scale triangles to be similar triangles, and they're going to have the same angles. Let's say if we say adjacent is equal to 1, that means equal to 1, that means that would imply that opposite is equal to root 3. Okay, so given this, there's not really a great easy way to calculate this. Like if we were to draw this out like this, and we know that this is 1 and this is like root 3, we'd pretty much be looking for the angle like that. Now, which angles do we know correspond to having having this? Oh, I see. Right. So, you see, imagine how let's try to find the hypotenuse here. And we know that we can find the hypotenuse fairly easily, because we know that the hypotenuse is going to be the square root of 1 squared plus root 3 squared, which is going to be 1 plus 3. And that means the hypotenuse has to be 2. And if the hypotenuse is equal to 2, and this is the right angle right here, this would mean, like, if we were to clone this, and we know that the angle here is 1, or I mean the side length here is 1, we could clone this triangle. Oops. Clone a reflected version. like this. So this is 1, this is 2, and this is 2, and this is 1. Like that. All of a sudden, we have to have an equilateral triangle. Be an equilateral triangle. Because, well, this entire side length is going to be 1 plus 1. That's 2. All the side lengths are the same. So the only angle that we can have in an equilateral triangle is 60 degrees, or pi over 3. So theta equals 60 degrees, or pi over 3. Okay, so I guess thinking back to some actual geometry diagrams can definitely be helpful in thinking about this, right? So I think, yeah, we used our knowledge of equilateral triangles and their properties. We used Pythagoras theorem to find the hypotenuse, and also use SOHCAHTOA to recognize that these are going to be the arrangements of our angles. Okay, so this is all super duper cool. Super duper cool. So we know that theta has to be 60 degrees through this process. You could also just ask your calculator, and that would probably be a lot easier, but you know, if you're not allowed to use your calculator and you have that type of test going on, well, this could definitely be another great way to address this type of question. Okay, so the above solution is good. Could be found with some graphical geometric analysis. Answer appears to come from direct mathematic evaluation. Cool. Okay, so here we have the next question on our menu today, which is asking us, how can we possibly express 0.63 as a fraction? 0.63, and as a fraction, well, we're going to have some whole number over some whole number. Like, in general, we want to avoid having decimals in our fractions. Yeah, so we know that any number, if it's just a number by itself, well, 0.63, we could rewrite this as 0.63 divided by 1. Divide anything by 1, and what do you get? Exactly the same thing. Okay, so this is technically a fraction, but we want to eliminate the decimal part of it, right? So we can equate this to, let's say we multiply the top by 100 and the bottom by 100, right? Because those 100 terms are going to cancel each other out. If we multiply the top by the same number as we multiply the bottom, we're going to have precisely the same fraction. So we can have 100 over 100 multiplied by 0.63 over 1. And, well, on the bottom, we'll have 100 times 1. That's 100. That's nice and easy. Now, 0.63 times 100, that just means we're going to shift over the decimal place by one spot and then another spot. So 2 spots that we're going to move over the decimal, and that's just going to be, well, 63 over 100. And that looks like a fairly reasonable fraction. Okay, now can we simplify this any farther? Well, it's not an even number, so we're definitely not dividing by 2. Now, is it divisible by 3? It is divisible by 3. The top is, but the bottom is not, so that's not an option. Not divisible by 5. The top is divisible by 7, but it's not going to be divisible by the bottom is not. So I would say, honestly, we are in simplest terms right now. So this is simplified fraction. Okay. Yeah. And oftentimes when we have a fraction like this, Most of the times you want to write them as percent, so most of the time write percent instead of dividing, or instead of denominator 100. Okay, so 0.63, we could clearly write that as 63 over 100, and we could also write that as 63%. Okay, so yeah, and as you can see, if you have 0 point something, well, just convert that 0 point into a percent, and that's perfectly valid as well. Okay, so that is how we can convert 0.63 into a fraction. Ain't that a beautiful thing? Okay. The above solution is good. Good job. Nice. Okay, so here's the next question that we have on the menu today. It is asking us how many cups are in 9 ounces, or 9 ounces added together makes up how many cups? Is another way that we can ask that. And to solve this question, it is really just a unit conversion situation. So whenever we have a unit conversion situation, we need a conversion factor. Okay, so this is our conversion factor. The conversion factor between cups and ounces, and I'm going to assume that these are both like volumetric stuff. There are 8 ounces in 1 cup. In 1 cup, which is equivalent. Another way that we can say this is 0.125 cups per 1 ounce. Okay, these are the same conversion factor. We can use either one and not be worried about it. Okay, so I think I'm gonna prefer to use this one because it's gonna be less to write overall. 8 is easier to write than 0.125, so that's the one I'm going to be going with. Okay, so to start this unit conversion, it says we're trying to convert 9 ounces and we want our result in cups. So we have 9 ounces. That is our given starting point, and we want to multiply it by the conversion factor in a way that ounces cancels out and we're stuck with cups. Okay, so we're going to reciprocal this. I'm going to delete that arrow. Reciprocal, and we're going to write 1 cup per 8 ounces. Now, we can treat these units as if they are kind of like variables, and we know that like anything divided by itself has to be 1, meaning that it's not going to be relevant to the calculation. So we can see that we have ounces on the top here and ounces on the bottom here. They have to cancel out, leaving us with just cups. So if we proceed with that, we will have 9 times 1, we don't need to write times 1, divided by 8, and this will give us our result in cups. And another way that we can write this is 1.125, and that's just converting 9 divided by 8 into a decimal. That will give us our value in cups. Or if you're a chef in the kitchen, it might be better to write this as 1 1/8 of a cup, because like you would get your 1 cup measurer, and then you would get your 1/8 cup measurer, and then you'd combine them. So that it's always convenient and it's always good to be able to convert between these different numerical representations of the same value, which is how many the cup equivalent of 9 ounces. Okay, so yeah, stay ready with these cancellation of units, and everything else in your life should be beautiful. Yeah, nice. the above solution is good. Awesome. Good job. Okay, so the next question that we have on the menu today is asking us, fairly straightforward, what in the world is going to be the result of this? The square root of 3. Okay, so typically when we have roots, simplifying roots, what we're going to want to do is we want to take the under the root, the radicand, under root, also known as the radicand, should be factored into as many components as possible, eventually get only a product of prime numbers under root, and you want to bring out the duplicates. Okay, so that'd be like the general procedure in simplifying a root. But as we all know, hopefully we all know, is that 3 is a perfect prime number. The only factors that 3 has is 1 and itself, or the only non-decimal, real integer factors that it has is 1 and itself. So, you know, we can't necessarily calculate this easily off the top. It would be honestly, I would suggest that you ask your calculator this. So we know that the numerical approximation of this is 1.73, I believe. And, you know, it's definitely got a lot more decimals behind it. But that is the approximate number. And we're at a point right now where we can't factor the under the root, we can't factor the radicand, so we are forced to just leave it as it is. We could leave it as just root 3, but you know, let's say you're doing some programming and you can't have that, and you need to have like an actual decimal value. Well, at this point, you really just need to like simplify it like that. Okay, so yeah, the amount of decimal places that you write is going to be, you know, it depends on the level of precision that you need. If you're doing something that is extremely high precision, like you're doing like nuclear physics, you're going to want a lot of decimal places. But if you're just doing this on like a math test, maybe like 1.73 should be pretty much good. All right, so yeah, fairly straightforward question with a fairly straightforward answer. So yeah, the above solution is good. Okay, so the next question that we have on the menu today is asking us what in the world is going to be the value of sine 15 degrees. Okay, there are many different ways that we can address this situation. The first most easy way, in my opinion, is just direct calculation. So the direct calculation, well, let me ask my calculator ASAP fast, is going to be 0.25881. And this is a decent answer, but this is not exact answer. not exact enough. Okay, if you just need this number directly, this could be good, but let's say you have sine 15 degrees and then you have multiple calculations afterward that all depend on this calculation. You will definitely run into problems if you just like round it right here. Okay, so and sometimes you can get away with it. It really depends on the context that you're in, to what degree this is acceptable to just put it directly into your calculator. Okay, another way that we can address this is graphically. So if we were to draw a sine function like this, where we have 180 degrees, 360 degrees, this would be 90 degrees, and suppose that our sine curve looks a little something like that. We know that, well, this is going to be 45, and this is about a third of this. Graphically we can see that it's going to be about 0.25. And this is approximately 0.25. This is honestly even less precise, but like if you're really in a pinch and you don't even have a calculator, this could be a good way to get an estimation. And as long as you know how to draw a sine graph with relative precision, you can get a decent estimate of what's going on. But to get the exact version, you definitely do not want to do it graphically. To get the exact version, you'll want to go through a process of trigonometric equalities or identities. Okay, so the main one that we want to use here is that we know that sine squared of x is equal to 1/2 1 minus cos squared of x. Okay, so if we have x is equal to 15, then we could rewrite this as sine squared 15 degrees, or instead I'll actually write this this way. So sine of 15 degrees, and we squared, because that's really what the sine squared means, is just like this. It's a little bit more clear, but a little bit tougher to write. Is going to be equal to 1/2 of 1 minus cos 2 times 15 degrees, which of course we know is going to be 30 degrees. Okay, so simplifying this even further, if we're going to isolate sine 15 degrees, we got to take the square root of the whole right side. So this will be 1 minus cos 30 degrees. So that's 2 times 15 over 2. That's just another way of rewriting it. And cos 13, even if we don't have a calculator, we can kind of imagine what that is off the top, because if we have a equilateral triangle, and we do something like this, we know that this has to be 30 degrees here, right? So let's say each had a side length of 2. This now has a side length of 1. And if we take this half of a equilateral triangle, chopped in half, this right here with Pythagoras theorem has to be root 3. This has to be 1. Hypotenuse has to be 2, and this is the 30 degrees that we're looking for. We know that cos of 30 degrees has to be the the adjacent over hypotenuse with SOHCAHTOA. So our adjacent in this case is root 3. Our hypotenuse is 2. So we could sub this in to our equation up there. So sine 15 degrees is equal to under the root 1 minus root 3 over 2, all divided by 2. And another way that we could write this is sine 15 is equal to under the root 1 over 2 minus root 3 over 4. Okay, so yeah, that's where this all came from. And yeah, we would get that same result here. Exactly. Yeah, so that 2, I think that's just a mistyping, because that is highly strange how that 1 became a 2. It could be equal, but what we have here is perfectly valid as well. Yeah. Okay. Nice. So, I trust my answer more because I'm not sure why that suddenly became a 2. But yeah, this is the answer that we came to with some trig identities and some algebra. We can come to a much more exact number. Of course, like we still want to send this to a calculator eventually, but you know, if we need high precision math, this would be the way to go. Okay. Oh, also plus minus. Because of the square root, we have to do plus minus. Okay, so yeah. So the setup of solution is good. Step 3. Oh, okay. Never mind. It makes sense. And these got to be they're going to be equivalent. I just know that. Right. Okay. So yeah, the above solution is good. Just had a lapse in my mental algebra for a second. To get from here to there, we pretty much just want to make this first term also have a denominator of 2. So 1 is going to be equal to 2 over 2. So that becomes 2 over 2 minus that. And then everything is nice and easy. Yep. Okay, very straightforward. Cool. So yeah, the above solution is good. Awesome. Different ways to write the same thing. Okay, so here is the next question that we have on the menu today, and it is asking us, what is the simplified form of the expression? Instead of reading that out, I'll write it out. Okay, so we have 5 multiplied, in brackets, we have 14 minus 12. All of that is squared, and we divide this by 2. Okay. I'm going to rewrite this as a fraction because, in my opinion, as you progress more and more through your academic life, you will see the division symbol less and less. You will see fractions more and more because fractions in general are less ambiguous, because if you have multiple divide symbols in a row, it can get sticky. Okay, so instead, the first thing that I want to do is 5 minus 14 minus 12 in the squared, and all divided by 2. And divided by 2 as a fraction instead of as a divide symbol. Okay, it just makes things a little bit easier. So the first thing that we want to do is address in bracket stuff. And that's the first thing that we want to do. And we know that the in bracket stuff, we have 14 minus 12. That's going to be, well, 14 minus 12, that's just 2. And 2 squared over 2. That's nice. So the next step, we want to do exponents. And if you look closely, you can see that we're doing the B in bed mass and then the E in bed mass. So it'll be 5 times 4 over 2. Because 2 squared, well, that's got to be 4. And then we do the multiplications. So the D and the M on the bed mass are actually on the same like hierarchy tier. But we'll do the multiplication first just to get like the top easier. We have 20, 5 times 4 is 20 over 2. And then division, which is just 10. So yeah, this entire thing simplified is just 10. Yeah, fairly straightforward. Now, how? Okay, so 14 minus 12 is definitely not 12. It's 2. Yeah, okay, so the final result of this is got to be 10. It's not going to be 360 because the in bracket stuff was just calculated wrong, but otherwise everything seems to be following the proper procedure. It's just somehow yeah, that was just calculated wrong, but these things happen. I've made mistakes sometimes. Even Isaac Newton made some mistakes. Even Einstein made some mistakes. So making mistakes does not make you silly. Repeating the mistakes makes you silly. Okay, so in the brackets, 14 minus 12 is not 12. Yeah. Okay. Okay, so the next function that we have on the menu today is asking us what is the domain of the function y equals the square root of x. Domain? What is the domain? Domain. So essentially the domain is which x values are legal inputs. Right? Because that's essentially what the domain is. What are we allowed to input into our function here? And let's think about this, okay? So the x has to be under the root, right? And we do not have any mention of like this seems to be just like a real number situation. So because only dealing with real numbers, under the root cannot be negative, but it can be 0. 0 is okay. 0 is good, though. Okay, so taking the square root of a negative number, you can't really multiply two numbers together to get a negative number, which is essentially what the square root operation is asking us to do. But 0 times 0, that's 0, so the square root of 0, definitely 0. Okay, so it seems that valid x numbers, valid x values, we have 0, and we have any positive real number. So that really just excludes the negatives. So the domain is that x has to be bigger or equal to 0. And that would be the domain. Okay, graphically, what that is going to look like, if we were to draw this function. So if this is our y, and perhaps this is our x. Whoa, let's go back here. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4. We would have a function that looks like this. Okay, 0 is good. But yeah, it kind of has like a fairly slow, kind of like curving downwards type of growth. But you know, the moment that we even try to cross the y-axis into the negative world, sitting on the border, sitting on 0, that's perfectly fine. But once we enter the negative world, we can't. It ain't gonna work out, Chief. We cannot take the square root of a negative number. It ain't gonna work out. So a domain that says x has to be greater than or equal to 0 is gonna look like this. We're gonna have values anywhere that is to the right hand side of the y-axis. Anything to the left hand side is in the negative world. That would be x is less than 0, illegal, inappropriate, not gonna work out. Only x bigger than 0. Okay, so yeah, that is the domain. Set of all positive real numbers. Answer should consider 0 in the domain because only negative numbers are out of the domain. Say all non-negative real numbers instead of all positive real numbers. Cool. So the next question that we have on the menu today is asking us what in the world is the square root of 5? 5. Cinq. That's 5 in French. So the square root of 5, typically when we're trying to simplifying roots, we want to see factor the radicand, which is under root value, as much as possible until only prime numbers left, till only prime factors and then bring the pairs outside. Bring pairs of factors out the root. Okay, so this is our general procedure for trying to simplify roots or like this. So since we're stuck here, because 5 is a prime number, 5 has no factors other than 1 and itself. Prime number, so we can't simplify this any farther. 5 is prime. Cannot simplify any farther. So the only thing that we can be left to do is now just directly evaluate. So now just evaluate directly. So you would just send this through your calculator. Under the root 5, it is, I calculated that to be 2.23607, on and on and on. That 7 is rounded, but it's an irrational number. So there, if you wanted to write out all the decimals, you would spend the rest of your life doing that, and you wouldn't even get it done. So yeah, 5 is a prime number. Can't simplify it any farther, so we can only evaluate it directly, or you could just leave it as is if you need that precision. So you would typically only want to convert roots to their numerical, like decimal versions, only when that's like the final step in your procedure. Like if I was doing like a lot of trigonometry, I would not want to have this as like an intermediate value. I would want to have the root for the maximum precision. Okay, so yeah, well, this is just a rounded version of that, just rounded differently, but otherwise the answer is good. So yeah, above solution is good. Beautiful. Oh man, last question. So time flies when you're having fun, as the old saying goes. So those are all the questions for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring the notification bell below. If you are interested in submitting your own questions, we have links in the description where you can get this. And if you're interested in getting tutoring, we have links in the description to help you with that. If you enjoyed today's video, please leave a like and a comment. And if you really enjoyed today's video, share it with your friends. This has been Millan from OneClass. I hope to see you again soon. I hope the mathematic magic journey that we went on today has been a fun time. I think it's been a fun time, and I hope you have an amazing rest of your day. Take care, have fun with the math, and math is cool.